Welcome to today's paper reading. Today's paper is titled, OLMoE, Open Mixture of Experts Language Models. This paper introduces OLMoE, an open mixture of experts language model, authored by Niklas Muennighoff and colleagues from the Allen Institute for AI and other institutions. The paper introduces OLMoE, a state-of-the-art language model utilizing sparse mixture of experts, MoE. OLMoE-1B-7B has 7 billion parameters, but only uses 1 billion per input token. It was pre-trained on 5 trillion tokens and further adapted to create OLMoE-1B-7B Instruct. The models demonstrate superior performance, outperforming even larger models like Llama2-13B-Chat and DeepSeekMoE-16B. The paper also presents various experiments on MoE training, analyzing routing to show high specialization. All aspects of the work are open-sourced, including model weights, training data, code, and logs, with links provided for access. Figure 1 illustrates the performance, cost, and degree of openness of various open mixture of experts, MoE, and dense language models, LMs. The models are categorized based on their active and total parameter counts, with MoEs denoted as model active total and dense LMs as model total. The number of intermediate checkpoints, #CKPTS, available for each model is also noted. The MMLU, Massive Multitask Language Understanding, score is highlighted as a summary of overall performance. Among models with similar active parameter counts, OLMoE-1B-7B stands out as the best performer, and is also the most open MoE in terms of availability of model weights, training data, code, and logs. The introduction of the paper highlights the significant cost and performance trade-offs in large language models, LMs. Despite their high performance, these models are often prohibitively expensive for many academics and developers. One solution to this problem is the use of sparsely activated mixture of experts, MoEs, which are more efficient than dense models. Industry-leading models like Gemini 1.5 and GPT-4 utilize MoEs. However, most MoE models are closed source, providing limited information about their training data and code. Prior efforts to make language modeling research accessible have been limited to dense LMs. To address these issues, the paper introduces OLMoE, a fully open mixture of experts language model. OLMoE is pre-trained on 5.1 trillion tokens with 6.9 billion total parameters, of which only 1.3 billion are activated per input token. This approach aims to make high-performance models more accessible and cost-effective. The OLMoE-1B-7B model is a decoder-only language model with NL transformer layers. The feed-forward network in dense models is replaced with a mixture of experts, MoE module, which consists of northeast smaller feed-forward network modules called experts. For each input token, a subset of K experts is activated. The model uses 1.3 billion active parameters out of a total of 6.9 billion, with 8 experts activated per input token. The routing algorithm used is dropless token choice routing. The adaptation strategy involves instruction tuning and preference tuning, incorporating datasets like No Robots and Daring Anteater to enhance performance on coding and math applications. Table 1 outlines the key design choices for the mixture of experts, MoE, model OLMoE-1B-7B. It highlights the active and total parameters, the number of activated experts per layer, and the routing algorithm used. The table also mentions the use of auxiliary losses for load balancing and router stability, which are integrated into the training loss function. The full configuration details are provided in Appendix B. Figure 2 provides a visual comparison of the architecture between dense language models, LMs, and mixture of experts, MoE, models such as OLMoE. The figure highlights the structural differences, focusing on the MoE module's activation process. Notably, it mentions that OLMoE-1B-7B incorporates QK-norm, a specific normalization technique, which is not depicted in the figure for simplicity. The MoE module's operation involves selecting a subset of experts based on a routing mechanism, which is a key aspect differentiating MoE models from traditional dense LMs. Table 2 outlines the composition of the pre-training data used for OLMoE-1B-7B, which includes a mix from DCLM and DOLMA 1.7. Key components are DCLM baseline, star coder, algebraic stack, AR14, PS2O, and Wikipedia. A filter is applied to remove documents with sequences of 32 or more repeated engrams. The training process involves 5.133 trillion tokens over 1.3 epochs, with a reshuffling and learning rate decay in the final 100 billion tokens. Table 3 provides an overview of the adaptation training data used for the OLMoE 1B7B model. The data includes a mix of instruction tuning and preference tuning datasets, with a focus on enhancing performance in coding and math applications. Key components of the dataset include additional code and math data, as well as the inclusion of high-quality subsets like no robots and a portion of daring anteater. This approach follows a standard adaptation recipe, which is crucial for successful model adaptation. During the pre-training phase, OLMoE 1B7B demonstrated superior performance across all tasks with significantly less computational effort compared to dense ALMA models. It matched or exceeded the performance of OLMoE-7B, despite using less than half the training flops and only 1 billion active parameters. Post-pre-training, OLMoE 1B7B was benchmarked on common downstream tasks, showing it to be the most economical choice among models with less than 2 billion active parameters. It outperformed several dense LMs with 7 billion parameters. After adaptation, instruction and preference tuning further enhanced the model's performance, achieving the highest average scores among the models benchmarked. This included notable improvements on tasks like GSM-8K and AlpacaEval, surpassing even larger models like Qwen 1.5-3B14B in certain metrics. Figure 3 showcases the evaluation of OLMoE 1B7B and the current best ALMA models during the pre-training phase. The key findings reveal that OLMoE 1B7B achieves better performance across all tasks with significantly less compute, flops, compared to the dense ALMA models. Specifically, OLMoE 1B7B matches or even outperforms almost 7B at the end of training, despite using less than half as many flops for training and employing only 1B active parameters. This superior performance is attributed to the dataset and modeling changes made to the ALMA setup, including MOE-related changes, stability, and performance improvements, as outlined in Appendix B. The evaluation underscores the efficiency and effectiveness of OLMoE 1B7B in leveraging computational resources during pre-training. Table 4 presents the performance benchmark of OLMoE 1B7B after pre-training against larger mixture of experts, MOEs, and dense language models, LMs. The comparison is made with dense LMs that have either similar active parameters, 1B, or total parameters, 7B, to OLMoE 1B7B. The model names include rounded parameter counts, distinguishing between MOEs and dense LMs. Notably, OLMoE 1B7B achieves superior performance among models with fewer than 2 billion active parameters, making it the most economical option for many LM use cases. It also matches or outperforms almost 7B, despite using significantly fewer flops for training. This performance is attributed to dataset and modeling changes, including MOE-related modifications, stability, and performance improvements, as outlined in Appendix B. Table 5 presents the performance of OLMoE 1B7B after adaptation compared to other models. Notably, OLMoE 1B7B, despite having fewer parameters, outperforms the chat version of Qwen 1.5-3B14B. The application of SFT and DPO tuning methods has significantly enhanced the model's performance across various tasks. The adapted model, referred to as OLMoE 1B7B Instruct, achieves the highest average scores among all benchmarked models, demonstrating its effectiveness and efficiency. In this section, we explore various design choices that led to the development of OLMoE 1B7B. We start with MOE-specific settings, where we found that MOEs can reach dense model performance with approximately 3 times fewer tokens. We also experimented with expert granularity, observing a 10% improvement in HellaSwag with more granular experts. However, shared experts slightly underperformed. Moving to general pre-training settings, our custom dataset mix, OLMoE mix, showed better results than DOLMA 1.7. We also found that a truncated normal initialization provided more stable training compared to a regular normal initialization. Additionally, using RMS norm improved performance despite being 15% slower. Finally, in adaptation settings, we discovered that not using load balancing during adaptation led to better performance. Using the post-annealing checkpoint also showed better results. We compared preference algorithms DPO and KTO, finding that DPO performed slightly better in our setup. Figure 4 compares the performance of a 1.3B parameter dense model with a 1.3B active, 6.9B total parameter mixture of experts, MoE, model, both trained on 128H100 GPUs for 130B tokens. The MoE model, which contains 64 experts with 8 activated and an FFN dimension of 1024, achieves the same performance as the dense model with an FFN dimension of 8192, but with approximately 3 times fewer tokens. Despite some memory overhead, the MoE model trains about 2 times faster. This controlled setup highlights the efficiency of MoE models in reaching comparable performance levels with reduced computational requirements. Figure 5 illustrates the impact of expert granularity on model performance. By varying the number of experts in tandem with the FFN dimension, the study ensures that active and total parameters, and thus compute cost, remain constant. For instance, with 64 experts, the FFN dimension is 1024 and 8 experts are activated, whereas with 32 experts, it is 2048 with 4 activated experts. The results show that more granular experts improve training loss, validation loss, and downstream performance. However, the study also notes diminishing returns with increased granularity, indicating that beyond a certain point, the benefits of further granularity are minimal. Figure 6 compares the performance of models with shared experts versus those without. Both setups use the same computational resources, but the model with a shared expert shows slightly worse performance. This is attributed to the reduced flexibility in expert combinations, which counters the potential benefits of isolating common knowledge in a shared expert. Figure 7 compares expert choice, EC, and token choice, TC models, both featuring an 8-expert mixture of experts, MoE, in every second layer. In TC, 2 experts are activated per token, whereas in EC, the capacity factor is set to 2. Despite these differences, both models utilize the same number of active parameters. The figure highlights the performance and efficiency trade-offs between these two routing strategies in MoE architectures. Figure 8 illustrates the process of sparse upcycling, where OLMoE 1B0724 is upcycled at 2 trillion tokens into a mixture of experts, MoE, model with 8 total experts, of which 2 are activated. The model is then trained for an additional 610 billion tokens. The figure compares this upcycled model to one trained from scratch for the same number of tokens. Both models use the same configuration, which includes some suboptimal settings that contribute to instability, such as the absence of QK norm and truncated normal initialization. The results, logs, and configurations are available at the provided link. Figure 9 examines the effect of applying a load balancing loss, LBL. The training loss graph does not include the load balancing loss for either model. The study reveals that using the load balancing loss results in improved performance, even after a few billion tokens. The load balancing loss, when not applied, no LBL, initially spikes but gradually decreases over subsequent billion tokens. This behavior is also observable in Figure 10. Figure 10 illustrates the expert assignment dynamics during training of a mixture of experts, MoE, layer, with and without the application of a load balancing loss, LBL. Initially, all tokens are assigned to the 6th expert, as indicated by the pink line. Over time, the model begins to assign tokens to the 1st expert, shown in yellow. However, the other experts, represented by the remaining lines, remain largely unused, suggesting they are dead weights in terms of GPU memory usage. This pattern highlights the impact of LBL on distributing token assignments more evenly across experts, which is crucial for optimizing model performance and resource utilization. Figure 11 illustrates the impact of adding router Z-loss with a weight of 0.001 compared to no additional Z-loss. The results show that incorporating router Z-loss enhances both the stability and quality of the model, as evidenced by reduced spikes in training and validation losses, and improved downstream performance. However, this improvement comes at the cost of a slight reduction in throughput, approximately 2%. The router Z-loss is employed in OLMoE-1B7B models with the same loss weight as proposed by Zoff et al. Figure 12 presents a comparison between OLMoE mix, our data mix described in Section 2, and DOLMA 1.7, which was used to train prior OLMoE models. The figure highlights that lower training loss does not necessarily indicate a better dataset, but rather suggests which dataset is easier for the model to learn from. The comparison shows that OLMoE mix leads to clear gains on all three downstream metrics, particularly on the MMLU benchmark. This result is attributed to the DC-LEM baseline dataset, which has been optimized through a series of dataset ablations targeting MMLU and other downstream metrics. Figure 13 compares the effects of normal initialization with a standard deviation of 0.02 and truncated normal initialization with a maximum/minimum cutoff of 0.06/0.06, corresponding to 3 standard deviations. The study reveals that truncated normal initialization leads to more stable training and better performance. Notably, the divergence between the two methods becomes apparent around 450 billion tokens, highlighting the challenges in pre-training ablations. This method is applied in OLMoE-1B7B. Figure 14 compares the performance of nonparametric layer normalization with RMS norm. It highlights that RMS norm leads to better performance in the model studied. This improvement is likely due to the nonparametric layer normalization causing a large number of spikes in the gradients, which is detrimental to model stability and performance. Figure 16 illustrates the total norm of gradients during training with either RMS or nonparametric normalization. Notably, the logging interval for the RMS run is increased at 75 billion tokens, which is reflected in the change of thickness in the graph. This comparison helps in understanding the impact of different normalization methods on gradient behavior. Figure 15 illustrates the process of decaying the RMS norm parameters. This figure provides insights into the adjustments made to these parameters over time. For more detailed results, logs, and configurations, the figure directs viewers to a comprehensive report available at the provided link. This resource is crucial for understanding the full scope of the experiment and its implications for the model's performance. Figure 17 illustrates the effect of decaying embedding parameters on model performance. It shows that decaying these parameters has only a minor impact on overall performance, with decaying being slightly more beneficial. This finding supports the practice of including embedding parameters in weight decay for simplicity, as done in OLMoE-1B7B models. Table 6 presents the load balancing loss calculated over a subset of corpora before scaling with the load balancing loss weight alpha. The table highlights that while load balancing loss is utilized during the pre-training phase, it is not applied during the supervised fine-tuning (SFT) phase. Interestingly, the load balancing loss actually decreases slightly during SFT, indicating a potential shift in how experts are utilized early in the training process. Figure 18 illustrates the effect of query key layer normalization, QK-norm, on model stability and performance. Both models in the comparison utilize nonparametric layer normalization. QK-norm involves the addition of layer normalization to the query and key projections. This technique is shown to enhance stability and provide a slight reduction in training loss. Further details and results can be found at the provided link. Figure 19 illustrates the impact of the Atom W optimizer's epsilon (EPS) value on model performance. The study reveals that reducing EPS to the recommended default of 1E08 significantly enhances performance while ensuring the run remains stable. This finding supports setting EPS to 1E08 for optimal results, as larger EPS values, while potentially more stable, result in smaller optimizer steps that may not yield the best performance. Table 7 presents the adaptation experiments of the OLMoE-1B7B model. It compares the performance of using the pre-trained checkpoint before annealing, the checkpoint after additional 100B tokens of annealing, and the checkpoint post-annealing with load balancing loss during adaptation. The table also details the application of direct preference optimization, DPO, and knowledge transfer optimization, KTO, to the respective supervised fine-tuning (SFT) model, highlighting the differences in performance metrics across various setups and tasks. In this section, we delve into the analysis of 4 key properties specific to mixture of experts (MoE) models. Firstly, we examine router saturation, which is defined as the proportion of expert activations at an intermediate checkpoint that match those at the final checkpoint. The formula for router saturation is given by router saturation T equals 1/n** sigma EET I intersection EET I. Our findings indicate that significant saturation occurs as early as 1% into pre-training. Secondly, we explore expert coactivation, which measures the proportion of times 2 experts are simultaneously activated. The formula for this is expert coactivation EI EJ equals NEI EJ/NEI. We found that there is no strong coactivation within a single layer, suggesting minimal redundancy. Lastly, we analyze domain specialization, defined as the proportion of tokens from a specific domain routed to a particular expert. The formula is domain specialization EID equals NK EID/ND. We observed high specialization in certain domains, indicating that experts are specialized in different types of data. Figure 20 illustrates the router saturation during the pre-training phase of the model, focusing on a random 0.5% subset of the C4 validation data. The saturation is calculated by comparing the routing decisions to the top K experts at 4 different intermediate checkpoints, 1%, 10%, 20%, and 40% of the total pre-training process, against the final pre-training checkpoint. This analysis reveals that the router's ability to consistently route to the same experts for given input data is already significant by the early stages of pre-training, aligning with findings from previous research. This early saturation is particularly evident for the top 8 experts, indicating that the model's routing decisions stabilize relatively quickly during the training process. Figure 21 illustrates the coactivation among experts in the OLMoE-1B7B model using a random 0.5% sample of the C4 validation data. The figure displays the 32 experts with the highest maximum coactivation scores, identified by their expert IDs on both the X and Y axis. Notably, there is no strong coactivation observed among experts within a single layer, suggesting minimal redundancy across different experts. However, Layers 7 and 15 exhibit similar coactivation patterns, with several groups of 3 or 2 experts frequently activating together. This observation indicates potential clusters of experts that could be investigated further for their specific roles in processing tokens. Figure 22 illustrates the domain specialization of 2 models, OLMoE-1B7B and Mixtral8X7B. The top part of the figure shows OLMoE-1B7B, which has 64 experts in total, with 8 experts activated per layer. The bottom part shows Mixtral8X7B, which has 8 experts in total, with 2 experts activated per layer. The figure visualizes how often tokens from different domains get routed to these experts at the end of pre-training. For OLMoE-1B7B, tokens are considered routed if they are sent to any of the K equals 8 active experts, while for Mixtral8X7B, tokens are considered routed if they are sent to any of the K equals 2 active experts. Horizontal gray lines in the figure represent the uniform routing probabilities, which are 12.5% per expert for OLMoE-1B7B and 25% per expert for Mixtral8X7B. This analysis helps in understanding the specialization of experts across different domains in these models. Figure 23 illustrates the vocabulary specialization of the OLMoE-1B7B model across different layers and experts. The left side of the figure shows the average specialization of each expert within a layer, while the right side uses dashed lines to indicate the average specialization of layer 7. The figure focuses on the first 32 experts out of a total of 64, with the data presented for K equals 1 as per equation 8. Additional data for K equals 8 and a comparison with the Mixtral8X7B model are provided in Appendix G. Table 8 illustrates the vocabulary specialization within the 7th layer of the OLMoE-1B7B model. The analysis employs K equals 1 as per equation 8 and utilizes a random 0.5% sample of the seed for validation data, excluding token IDs that appear fewer than 10 times. This approach helps in identifying the specific vocabulary terms that the model specializes in at this layer, providing insights into its linguistic processing capabilities. In the realm of mixture of experts, MoE advancements, current large models predominantly adhere to the transformer architecture with minor modifications like decoder-only training and SWI-GLU activations. MoE layers, though still under exploration, have seen improvements in routing techniques and expert segmentation. On the topic of open large models, LMs, various families exist, categorized by the openness of their weights. Fully open source models, which include not just weights but also training data and code, are crucial for scientific research and broad distribution of benefits. OLMoE 1B7B is introduced as the first fully open source, state-of-the-art MoE-LM. In this study, the authors have open-sourced two models, OLMoE 1B7B and OLMoE 1B7B Instruct. These models, with 1 billion active parameters and a total of 7 billion parameters, have demonstrated state-of-the-art performance, even surpassing larger models such as DeepSeekMoE-16B and Llama2-13B-Chat. The authors have also detailed their contributions, with Niklas Muennighoff leading the project, Luca Soldaini creating the pre-training dataset, and Dirk Groeneveld providing crucial advice on stability and throughput improvements. Thank you for watching.